discussion of CH substitution. Again, focusing really on chlorine and bromine as the synthetically useful reagents. We'll look at why chlorine is more reactive and bromine is more selective in these reactions. We'll go over some examples of starting materials that are achiral to begin with, but once you substitute, how they can become generate stereocenters. So they'll kind of relate to the quiz in terms of counting isomers. And we'll look at stereochemistry of radical reactions, and then the majority of the lecture is really going to be focused on allylic bromination. It's still a radical substitution process, but it uses a different reagent, and the mechanism is a little bit different. So as we explore that, we're going to again put all of these concepts together in figuring out what gets substituted, is it going to generate a stereocenter, and then again, how do we differentiate all of those things? Any questions prior to starting here? Okay, so as a summary slide, we looked at those examples of comparing tertiary versus secondary versus primary hydrogens in the CH substitution. We also talked about what's a benzylic or what's an allylic carbon in those radicals, how they're stabilized. So again, we'll have a figure in which we look at all of the radicals compared and graphically see which CH bond we're going to cleave first, because that's ultimately what we're trying to figure out. Again, fluorine's way too exothermic for this, so essentially anything can get fluorinated. Iodine does not have enough energy in the propagation step 2 to supply to propagation step 1 to be useful. And so that leaves us with the chlorine and the bromine. And chlorine, again, supplies enough heat from step 2 for step 1, but it's almost too much heat. So we have this issue of reactivity versus selectivity compared to bromine. So in trying to further understand the trend of tertiary versus secondary versus primary, we'll look at a table referring back to the bond dissociation energies to calculate some values, and then we'll just generate a plot to see that visually. So again, I can't stress this enough in terms of the term. We're doing substitution. So CH going to CX, where that's chlorine or bromine. And then as we move on in the module, that X is then going to be substituted. I'll call it NU. So that's a further substitution. And NU means nucleophile. It's some other reagent of all the functional groups that you know, where a halogen is going to become a different functional group. So to understand reactivity, so say chlorine versus selectivity bromine, I created this table, and I don't remember the exact values we'll fill in, but they're on the next slide. But the way it's set up is you have your hydrogen type, primary, secondary, tertiary. So these will be different values, say A, B, and C. And then the HCl value is the same going down that column. So like D, D, and D. And then the third column, we're just adding the numbers together. For bromination, we'll use AB, C again, and then the different value for HBr we'll say E. And then again, these values will give us an indicator of why there's a difference in these classes of CH bonds. So there they are. And again, the number values come from the table of bond association energies. So if I can highlight here in red, notice for both chlorine and bromine, the CH values down those columns are the same. So a primary is plus 421, a secondary is plus 413, and a tertiary is plus 400. Then for HCl, notice all of those are negative 432. And then in that third column for the change in enthalpy, we've just added them together. And so since they're all negative, I highlighted them in green, which basically means that in that radical chain mechanism, again, step 2 is always supplying enough heat for step 1. So the chlorine radical is kind of indiscriminate about which type of hydrogen it will abstract. What's different now for bromine, so again, that value changes to negative 366. Notice these values in that column are all positive. So you have plus 34, plus 47, plus 55. Again, that means you're starting from 0 and you have to go up. So for tertiary, you would hit plus 34 before you hit anything else. So for when you use Br2 as the reagent, it's easier to cleave a tertiary bond than anything else. And so again, on the next slide, we'll plot that so you can see the differences in those two things, reactivity and selectivity. Yeah.
Does that mean that the primary, the 1 degree bond formation is the easiest to set?
You probably want to think of it a little bit different in terms of like nature. So again, as humans, we just throw this stuff in the flask and it happens. In terms of 0 going down, yeah, you hit negative 11 first. But in terms of like nature, negative 32 evolves the most heat. So that gets you sort of lower in terms of energy. So as we introduced maybe a lecture or two ago, these reaction coordinates, for the purposes of this class, it's really just qualitative. And so I'll run through the couple different points on the slide and how you're looking at sort of the levels of where those points are. So we're going to use 2-methylbutane as our test case, because this has those primaries, those are equivalent, a different set of primary, secondary, and tertiary. So it's covering all the bases there in terms of what could be substituted. So if I draw a line here, I would say, okay, that's our starting material. And I'm going to draw a dotted line for reference purposes. And so notice from that starting energy, you're going uphill. So that the very top is called the transition state. And for lack of not being very eloquent, all I'll say is transition states can be weird because they're not necessarily going to obey your normal Lewis dot rules in terms of 4 bonds to carbon, that sort of thing. You have bonds making and breaking at the same time at that point. So carbon could have potentially 5 things bonded to it. But the thing to keep in mind, because it's at the top of that hill, if you draw a line down to the x-axis, which is a time axis, that point does not span a lot of time. So it's not like seconds or hours or days. I mean, it's like pico or femtoseconds. So like 10 to the minus 12 or 10 to the minus 15 seconds. So, I mean, it's like boom and it's gone. But it does exist for a short amount of time. So transition state is the highest energy on the coordinate. And from there, it's going down. And then it hits a well. And so notice there's our different radicals. So we have a primary, a secondary, and a tertiary. So those can exist in those 3 different wells. And if I arbitrarily sort of pick 2 points of the well, and I draw those lines down, you can see that that exists for a much longer period of time. So these have a different name. They're just called intermediates. And that means if given the choice, it could go this way or that way. Even though it's drawn as like a flat sort of graph, if you imagine you're sitting in that well, it could go down that way one path or this way another path. So it's almost like 3D instead of just a slice. And so the question was asked, in terms of like this line right here, as you go down, yeah, you hit -11 first, but -32 is more stable because more heat has been evolved. So in the comparison of this energy versus that one, this one's lower. And so that was for chlorination, where everything is, see how these energies are below that line? For bromination, on the right-hand side of the slide, from your starting material point, notice now you're going uphill to the transition state, but the intermediate is also further higher or uphill than the starting material. So these points so that's uphill, and that's still above. So that's why this number here is plus. So if this were you, and you had a choice between climbing those 3 hills, which one would you choose? So you'd pick the lowest one. So that's, you can call it laziness or whatever, but I mean, you want to expend the least amount of energy on what you do, right? And so that's essentially what nature will do, is it's going to climb that hill because it's the easiest. And what it's telling you is that tertiary radical is the most stable. So that's the one that's preferentially formed. And again, depending on how you learn best, whether it's the numbers or the graph, they're telling you the same thing. So just to recap, chlorination is reactive because really any of these paths can be followed. Bromination is selective because it's going to take the path of least resistance. So if there's a tertiary, it will go after that. But if there's not one in the molecule, it will go to secondary. If there's none of those, it will do primary. So to add a little bit more detail, to get to the transition state, so we just typically call it TS, transition state. That energy, so the change in energy of activation is always positive. Which means that it's always going to be above the level of your starting material. And the reason for that, if you look at this structure I've drawn, again, so this would be sort of partial making, and then that bond's being partially broken. So on the time scale, if you could like keep zooming with your fingers on the time scale, eventually you would get to see that transition state where you have bonds partially making, partially breaking. It's not like it just hops off from here to there. There's still that process that happens. And then once all of that occurs, then you get to the intermediates. So as I said, intermediates will always be in a well. And then more stuff can happen. Eventually you'll get to the products. And so overall you look at, is the product energy higher or lower than where you started? That gets you the overall energy for the reaction. Any questions before we move on? So here are the different types of radicals as plotted, of increasing stability versus energy. So in reading from left to right, this carbon radical is associated with an sp hybridized carbon. So notice its energy 547. And then let's look all the way to the right here. That carbon is sp2 hybridized, but the radical exists in a p orbital. So that's the normal situation. And its energy is plus 369. So again, if you're thinking you're starting at 0 and you go up, that's the first number you would hit. So what we're really concerned about, if I can draw a line like right here, everything to the right of that line comes from a carbon atom that was originally sp3 hybridized. When the radical's formed, it changes hybridization to sp2, and then the radical exists in the p orbital. And so those are the most common. So to the left, what I just underlined is telling you the radical now exists in an sp2 orbital or an sp orbital. And that helps explain why it's higher in energy. So as you look at a molecule, you're looking to classify the types, and the less energy you put in to get to one of those types, that is telling you that's preferentially going to be substituted. Any questions? So now we'll talk a little bit more about stereochemistry, because the issue, as I said, you're going from sp3 to sp2, so the carbon atom in that radical intermediate is sp2 hybridized, and the radical is in the p orbital. As you see in the drawing here, so there's your halogen. It's abstracting a hydrogen. So we use the fish hook arrow to indicate that. That carbon's sp3. It now becomes sp2. And for lack of a better way of communicating it, the dot is the unpaired electron, the radical. But what you have to keep in mind, since that's a p orbital, that unpaired electron density exists in both the top and the bottom lobes. So even though the dot is just shown there, it's in both places at once. So if you can imagine, if you had, I'll say R1, R2, R3, if you had 3 different substituents, and then that carbon radical abstracts a halogen to become a CX bond, that's now generating a stereocenter. And so you would get, if it went from the top face, or if it went from the bottom face, you're going to get a 1-to-1 mixture of those stereogenic carbons. And again, that's called a racemate. So let me just write this while I'm thinking about it. So the radical intermediate is achiral, therefore it must generate the racemate. You will not favor R versus S, because there's nothing around it that will discriminate which face gets halogenated. So now that we have the basics, let's sort of put this into context and look at a couple problems. And so we have one methylcyclopentene, and I've identified three explicit hydrogens, A, B, and C. And it says order them according to increasing bond strength. Again, it's October 30th, your finals, like what, December 6th or 8th or something like that. So you got about a month, taking out Thanksgiving because you'll just be eating turkey at that point. The ACS final will use questions that are worded like that. So again, you're organizing things according to some trend, and then you have to pay attention to like this or that, less than or greater than. Does it match that word that's in the question? So by increasing, we want the weakest bond listed first and the strongest bond listed last. So when we look at A, B, and C, the first thing I would do is just write the hybridization of the carbon next to those things. So sp3, sp3, sp2. So that means HC must be listed last. Does that make sense? So we can eliminate choices A and C. And then at this point, the next thing to do would be classify the type of CH bond between A and B. They're both secondary, and then that would tell you, okay, there must be something else that differentiates them. So B can be further differentiated because it's allylic. So there's a double bond. An sp3 hybridized carbon bonded to that double bond is the allylic position. So that one's allylic, which means when that forms a radical, it can be resonance stabilized. So that's the weakest, so that should be first. So when we look at choices B versus D, it looks like B will be the correct answer. And so once you've done that, really what it's telling you is, okay, HB is going to get substituted preferentially. So we'll do some problems where we consider stereocenters, and then we consider allylic carbons, and then substituting those specifically. So there's our test case there, 2-methylbutane. We're going to use chlorine, and we just learned that, chlorine supplies enough energy to do a substitution basically at any of those positions. If we were using bromine, it would essentially give you one major product where only the tertiary is substituted. So 2-methylbutane has 4 unique carbons, 4 unique sets of hydrogen. So 6 to 3 to 2 to 1. And again, what that's informing you, if I drew the class under them, so those would be primary, secondary, tertiary. So that's further informing you. You would at least get 4 monochlorinated products. But again, now the issue is that number can be larger if when you do that substitution, you're generating a stereocenter. So I'll try to work around the prompt here and make it a little bit more interactive. So these methyl groups here and here, they're equivalent. If you did a CH to CCl substitution, would that generate a stereocenter? Huh? Getting some head shakes. Let's draw it out so we can see. So it does not generate a stereocenter there, but it makes that a stereocenter here, right? Does that make sense? Because now this carbon to begin with, it has 2 methyl groups, so it's achiral. But now you've differentiated them, so that can become a stereocenter. So this tertiary one, if you substituted that, does that generate a stereocenter? So that would be no, because you still have these 2 methyl groups bonded to it that are the same. What about substituting at the secondary? So that would be yes, because then you would get Cl, H, methyl, and then isopropyl. And then finally, the last set, this H, from the methyl, if you substitute that, you're going to have 2 H's, but then nothing else is really differentiated, so that will be no. So if we count, we have 1, 2, 3, 4, wait. 1, 2, 3, 4, 5, 6. And I hope that sort of impresses upon you that this would be a reaction that you would not want to run, because you have 6 compounds in there. They all have the same molecular weight. Nothing really differentiates them in terms of probably a boiling point that you could separate them. So you'd have this mixture that would be a nightmare to purify. And so that's, one of the reasons why bromination is more effective, because it's more selective in what it's going to substitute. I think we sort of already answered this. I'm going to skip that, just so we can do some of this review here. So of the 2-chloro-3-methylbutane, we said that carbon 2 would be a stereocenter. So what ratio of R to S enantiomers would be formed in that? I'll invoke my high school algebra teacher, Mr. Tiber. How much? How many? So the intermediate, again, is achiral. So intermediate. So when that radical reacts with chlorine, it will do it from the top and the bottom face equally. So you would generate a 1-to-1 mixture of R and S. So here's one of those enantiomers. And so really what we're asking is as it's drawn, is that carbon 2, is it R or S in terms of the CIP nomenclature? And the hydrogen's coming out towards you. So you have an H, a Cl, and 2 carbons. Hydrogen's priority 4, chlorine's priority 1. Then of the 2 carbons that are directly bonded to it, so this one and that one, this one will get priority because it has 2 other carbons, and this just has hydrogens. So we get 2 and 3. I know we're getting a lot of numbers on there. The red numbers are the numbers for the name. The blue numbers are for the stereochemical analysis. So we're going 1, 2, 3. So that's clockwise R. But since the 4 is towards you, this has to become S. So that will get us B as in boy. Yeah.
So why would it not be D and you just split the numbers?
So that's like in the nomenclature rules, that's probably like if you were in Microsoft Word, you would like tab over like 3 times and say this is like a sub rule. So in terms of the nomenclature, C comes before M, right? And then if you're assigning the numbers, I think you put the lowest you then go in like just numerical order. You know what I mean? So here's another problem that was related to the last quiz in a sense. So there's methylcyclopentane, and it's asking how many monochlorinated isomers there can be. So all of the carbons are sp3 hybridized, so that we essentially have to consider every unique H set then. So there would be 4 of them. We have a primary, tertiary, and then 2 different secondary sets. So at a minimum, there would be 4 monochlorinated isomers. But again, that number can be greater after once you do the substitution and then sort of the stereochemical test. So let's, I guess, see what we can see. So if we substituted off the primary, we would get that. And then does that generate a stereocenter anywhere in the molecule? So not really. So that one does not either. Essentially, the molecule has a mirror plane. So what about that one? So how many stereocenters does it have? So it ends up having 2. So this is probably the easiest one to spot. But now that other carbon bearing the methyl group, that becomes a stereocenter. And we said for every n stereocenters, there's 2 to the n stereoisomers. So total right now we're up to 6. Because again, keep in mind, each stereocenter can be R or S, so you could have R, R, S, 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 R, R, S. And then the last secondary set. So again, that would be a stereocenter, and then that would be a stereocenter. So total, the answer would be 10. And conceptually, you could differentiate them just using uniqueness. That's possible, but practically speaking, it would be a nightmare to separate those things. And again, the goal for any reaction is to produce one thing in 100% yield. Any questions before we dig in a little bit deeper to this as a review? So there's 1-chloro, 1-methylcyclopentane. Do you remember what a meso compound is? Huh? So that's one criteria, but there's probably two more criteria. So a meso compound, it has to have stereogenic centers, and then it must have an internal mirror plane. And so therefore it will not rotate plane polarized light. So this is not a meso compound because there's no stereo center, so it doesn't pass sort of the first checkpoint. So we said that once we substitute a secondary CH, we then generate these two stereo centers, so we get 4 stereoisomers. There they are. Again, the bolded wedge is coming out towards you. The dashed line is going away from you. So this compound is asking you which one is the 1R, 2R. And then you can orient yourself according to the nomenclature. So the chlorine's at position 1, the methyl group is at position 2. So you don't really have to do all 4. We're just going to start with A, and I'll show you how you can, through process of elimination, get the right answer. So again, in preparation for the final, even though you might get, holy shit, like those are 4 things I got to put like 5 minutes of time into. If you understand sort of the algorithm for problem solving, we'll do A, and then we'll find out that the answer is C. So let's start with, so chlorine is at the 1 position, and the 1 position has to be R. So let's assign priority here. So chlorine is going to get 1, hydrogen's 4. So now you have these 2 carbons. The top one is differentiated because of this extra methyl, so that's going to get priority. So 2 and then 3. And then if you do that, that comes out counterclockwise, so that's S. So what that's telling you is D has the same configuration for that chlorine, right? So we can eliminate A and D. So you don't even have to worry about D. So with the other one, the methyl group is at the 2 position, so that also has to be R. I'll do these numbers in green here. So 4 is the lowest priority. Now we have 3 carbon atoms, so we have to differentiate them. The carbon bearing the chlorine will get priority 1. Then you have the ring carbon and then the methyl group. The ring will get priority 2. And then the methyl gets priority 3. So when we do the 1, 2, 3 there, that's clockwise. That should be R. So that methyl group has to be the bolded line. So that's going to get you C. So, even though that took a couple minutes, again, if you understand the logic and you develop the intuition, you can significantly increase your speed per question on the final. So the final is 70 questions. I think you get something like 2.2 minutes or something per question. So if you're stuck on question 3 for like 15 minutes, or I kid you not, a student fell asleep for like 35 minutes during a final once, move on. That's my advice. Just circle back to stuff that you don't get or you're ambiguous about. It's in your best interest to answer all of the questions. So here is a question related to relationship of stereoisomers, but you're not given structures, you're just given the nomenclature. 1R, 2R, 1R, 2S. What is their relationship? So they need to be diastereomers because the 1R is staying the same and then the 2 position is changing. So again, to be the enantiomer of this would be 1S, 2S. The enantiomer of that is 1S, 2R. So each position must be the exact opposite. So look at these numbers now. 1R, 2R, 1R, 3R. So those have to be different. And they're different because this number right here, that's changing. So the enantiomer of this, again, would be the 1S, 2S. This would be 1S, 3S. So we got 5 minutes. We probably won't get through all of this, but I do want to introduce it. Yeah. Okay, so another set of conditions. Now again, we're slowly ramping up in terms of the amount of material, and this is typically where you'll form your opinion about the difficulty of the course. As we start learning the reactions, now we're going to learn a lot of reagents. So the reagents are the things that carry out the reactions. But really what grounds you is identifying the functional groups and the reagents they react with. So however you do that with index cards or concept maps, that sort of thing, you'll really want to start doing that so you don't feel overwhelmed about just the amount of information that we're going to go through. So we had said the allylic position was special because once that bond cleaves, we can form a resonance hybrid where that radical density exists at either position 1 or 3 of the hybrid. So the molecule that's shown is propene, but you can imagine as you start sprouting other stuff off that double bond, it gets a little bit more complicated. So that has the weakest homolysis energy of plus 369. And so you can cleave it pretty easy and substitute it. Again, as we'll see either today or Friday, once you start putting other things off this double bond, then it gets a little bit more complicated. But the new reagent on this slide is called NBS, which is N-bromosuccinimide, and it's shown right here. So the N stands for nitrogen, the B stands for bromine, and then the rest of this stuff here is the succinimide. And so it ends in IMIDE. Notice that is an amide, that is an amide, and so two of those centrally bonded to something is called an imide, with an I. And this reagent is used as a surrogate for bromine because it's a nice solid. Bromine, have you ever seen like Br2? Bromine itself is a liquid. Like if this can was filled with bromine, it would be like 5 times heavier than and you would see like brown fumes coming off it that smell like the community pool. So it has a really strong like antiseptic smell. And that can be dangerous to handle because you don't want to breathe it in. You don't want to spill it because it's so heavy. So this reagent is a solid. It's easy to weigh. It doesn't have the same safety concerns. And what it will do is cleave this bond, the NBR bond, pretty easily with light or heat to generate a bromine radical. And I think we'll wrap it up here, but then we'll look at that bromine radical, how it's going to start scanning the molecule for allylic CH bonds.